7/8, everybody's getting engaged, and then we'll then have the corporate discussion. So our first question, where are the flood boundaries in the fossil record? And the reason why we're going to treat this one together is I want to walk you through what is the most common way of interpreting the fossil record in the context of a global flood, and then some variations on that theme. So if you remember back to our geological time scale, we basically had 3 eras. We have the Cenozoic, we have the Mesozoic or Mesozoic, and we have the Paleozoic. And then within each of these eras, you have periods that you can split them into. And so the Paleozoic, you can split it into 6 roughly equal in length periods. The first of which is the Cambrian, then the Ordovician, the Silurian or Silurian, the Devonian, the Carboniferous, and lastly the Permian. The Mesozoic we can split into 3 roughly equal periods. There's some flexibility in that. First is the Triassic, then the Jurassic, and then the Cretaceous. And then this one, basically you split into 2 periods, which few people ever do, or you can separate it into a bunch of what are called epochs or epochs. Okay, and so the first of which is called the Paleogene. And then we won't talk too much about these up to what is the current epoch, the Hologene. Okay? And so we've got some other epochs in there, but it doesn't apply a whole lot to what we do in this class. We talked a lot about forms showing up in some of these periods. What you're talking about are modern forms showing up here. A lot of our animal phyla already have representatives way back here. A lot of our plant phyla already have representatives, somewhere in these Paleozoic or Mesozoic. And so, if you want, I can give you the other epochs. You can find the other epochs. But this is a good kind of a foundation of the geological timescale at this point. And then the question is, well, what should we consider? And then here, I guess I should include this. These would be collectively referred to as Precambrian. There are other eras, but anyways, just collectively referring to these as the Precambrian is good for your understanding. All right, so then there's a question of, okay, well, if we have this geological time scale, where would we imagine that there was a global flood? How much of this rock layer is made up by deposits that would have been laid down during a global flood? The most common interpretation of the geological timescale from a flood model is that everything from the beginning of the Cambrian to the very end of the Cretaceous are flood deposits. That is the most common interpretation of the geological timescale from an idea of having a global flood, something along the lines of what Scripture describes in the Genesis account. Was it Genesis 6 through 9? Maybe even into 10. By the time you get to 11, there's the Tower of Babel. So what we're talking about here, this basically what we would do is we would look at this then as not really an accurate history of what was going on there, but rather there's the order of events or the order of environments destroyed during a global flood. Okay? Now there are some modifications to this theme. Some, and actually many, will draw this boundary up here. Some flood models will draw this boundary up into the Cenozoic a bit. Where still most of the Cenozoic would be considered to be post-flood deposits. But some of these models, and this is why I did a dotted section here, some models do take this boundary beyond this one right here, which is called the KT boundary. And then, we talked about this before, but a lot of these boundaries are marked by events where a lot of the diversity disappears and then with time gets replaced by other forms. And so the KT boundary is not the most dramatic of that loss of diversity, but it is the saddest. It's a place where a lot of your dinosaur forms cease to exist. It's a place where a lot of your really cool early mammal forms cease to exist, and a place where a lot of your really cool early bird forms cease to exist. It's kind of a sad boundary. The worst is right here. Bless you.
Thank you.
This one is the most dramatic, and this is called the PT boundary. And then the last asterisk I'll put up here, or some kind of a symbol. We'll do a cross. And this would be the Cambrian explosion. Okay, so the most common idea of a flood model is that it stops right here at the KT boundary. Some push it up into the Cenozoic a bit, but still most of the Cenozoic being post-flood. And then some, very, very rare, put the beginning of the flood like a bit into the Paleozoic. Allow the first portions of the Paleozoic to be pre-flood deposits. Just kind of keep that in mind for future, because you may, in fact, interact with somebody that has that view in the future. Because, anyways, that's another thing for another time. And so this is kind of the idea of how you would interpret the fossil record from an idea in which what the Bible describes as a global flood is an actual historical event. And so a good portion of the fossil record, so based on, geological time, this would be about 65 million years ago, where you have this star. And so from here down to the Cambrian accounts for about 500 to 550 million years of time. So by this idea, most of this geological column was formed during the global flood. And rather than accounting for 500 to 550 million years, rather represents, the amount of time described in Scripture. It should be 40 days of rain, and I forget the total number of days where water is on the earth. Yeah.
Is 550 million years from now till the Precambrian, or was it from the...
No, yeah, so this is from now to here is about 550 million years. So the difference in time between 65 and here is somewhere between 500 and 550 million years of time between these two boundaries. But then from current to here is about 550 to 600 million years. Yeah.
And then where's that dating come from? Does that come from, we pulled this fossil out of this rock? And
You mean those dates of
How do they determine how old those periods are?
So you do it by radiometric dating. You've got the most of them. Potassium-Argon dating is a common one, in which a particularly unstable form of potassium degrades into argon with a predictable half-life. And so if you go and you take a rock from one of these deposits and you determine the argon to potassium ratio, you should be able to match it with what the half-life of that unstable form of potassium is.
Okay.
Yeah. So most of it can be done So here, to answer your question, I will say most of it is done based on just what you assume that deposit is. And so if you're going out and you're digging at a site and the conventional idea is that those are Ordovician rocks, you won't test any of those rocks. You'll just assume that those are Ordovician rocks. However, if you would take some rocks and you were to date it, you'd probably be able to confirm that it's fitting inside of that area.
So is that different than like carbon dating?
Yeah, well, not necessarily, but it's different because carbon-14 has a very short half-life. Carbon-14's half-life is a little bit over 5,000 years. The unstable form of potassium's half-life is, I think, 1.2 billion years. So in scales, yes, but in terms of the mechanics of how you do it, no. But you can't use carbon dating for anything older than about 10,000 years or so, because then its reliability is really going to start to
So the
deteriorate.
dating is still pretty accurate then? Arguably?
Let's say precise. The dating is precise in that all of your measurements should give you relatively the same value. Whether it's accurate implies it's true.
Okay.
Right?
Yeah.
So is it accurate? Well, it depends on how old you think the Earth is. If you think the Earth is 4.2, 4.3 billion years, then yeah, you would say that there's a high level of accuracy.
Because the dating is consistent in the way
Yes.
it's touched out, but we don't have anything to compare with to determine if it's
Sort of, yeah. I mean, we can talk about radiometric dating techniques, but that's a different discussion for another time. You'll probably talk about that next semester in Gen Chem. I don't know how much, but you might. Okay. So, are there any questions right now on flood boundaries? Okay. So just to kind of put this in context, the idea is that chimpanzees and humans, most recent ancestor, dates to about 11 million years ago. So which would be, a sixth of the way through the Cenozoic, heading backwards, long after this KT boundary. Okay? So most of the familiar forms that you think of when you think of animals don't appear until post-flood deposits. Most of those common forms that you think of. All right? Okay, so right now I'll give you the first question, our lecture break question. You'll assemble yourselves into groups of 6/7/8. You will elect a leader, and that leader will get everybody involved. And please do groups of 6/7/8, but if you really don't want to, I guess I can't make you. But yeah, there's a reason why I give those numbers. So the first question, how can we explain the sudden appearances of several phyla? Okay, the sudden appearances of several phyla. So it doesn't just happen at one point in the fossil record, but it happens several points in the fossil record. And as you're addressing these questions, it would be helpful if you came up with some thoughts about how do we explain that from this idea of a flood idea of the fossil record, but also how would you explain it as there is no global catastrophe, but instead what you're representing is a regular, roughly stable account of Earth history. And the reason why I say roughly stable is you have to have some kind of a catastrophe to bury living forms and fossilize them, but you could have local catastrophes and not global, which is a big difference. Big difference. Okay, so as you're thinking through that and talking through that, come up with two different explanations, if you will, for how you would explain that. All right, go ahead and take 2 or 3 minutes, get your groups assembled, get yourselves a leader, and talk through this question.
Yeah, you just have to sit there and let us talk.
Okay.
All right, Kimmy.
I don't have any thoughts yet.
Rachel?
Yep, that's accurate. I love that thought. Yeah, let's go with that.
Oh, she gets to speak. Oh, Jonathan. All right, anybody else? Maybe something more profound?
Man, profound? That's asking a lot.
It is, kind of. If you're sleeping, it's profound.
I mean, sudden appearances of several different, phyla. It's like, okay, if we're looking at it from the flood perspective, you're gonna have
So basically, we want to look at this from
a lot of like
flood happened, and we also look at it from
disruption in the fossil record. You're gonna have a lot of layers building on top of themselves.
Right.
And whatnot. And so, like, if you have maybe a group of organisms in different parts, and then
We'll start up here.
you'll see in the fossil record how you'll have several different phyla
Is this referring to like
pop up.
deposits?
Yeah, like deposits.
Maybe like they had a similar environment, like maybe they might have been in different places around the world, but that all got hit by the flood at the same time.
Yeah, and then kind of bury them in kind of similar places in the fossil record.
I have to remember I'm not leading this. 'Cause I don't know, it's like- oh, okay. So basically different ecosystems.
Yeah.
Okay, I would agree with that. Some people would argue that it's different altitudes.
No. I mean, if it's
but
different
if it's
altitudes, you're gonna, if there's water, you're gonna have a mixture of the water.
Right.
So
So
you're
it'd be
not-
different ecosystems and
and so if
different
they have the same,
different animals are represented in different ecosystems, like you have today. There are some more complications with that as well, because what do you do about marine animals? Because you do see a certain amount of change throughout marine animals. You do not get placoderm fishes past, I think, the Ordovician or the Devonian. And a lot of their changes like that. And so how do you understand that when usually marine animals are very, very cosmopolitan? So blue whales, whatever, today are around the world. Killer whales are around the world. So, but basically different environments. The older perspective would be as different animals evolve over time, we see them appearing in the fossil record. And it seems to indicate that evolution happens in spurts. It happens really quickly due to environmental changes or whatever. And then it comes to an equilibrium and it stays there, and then another change happens, and then animals evolve to react to that. And that's how you explain that in the older perspective. But anyway. No?
Do you want to share that with the help?
I did. Yes. Okay.
So like in the sense of like if you have several phyla, the event species like evolution.
Are we talking about like several phyla as in like different, or is it like a polytomy that, are we explaining why polytomies pop up?
No.
No,
You don't need to
okay.
think about this in terms of a
Okay.
phylogenetic tree.
So one
Got
hand,
it.
it seems at the phylum level though, all the phylum that's represented within Animalia appears in the Cambrian. So are we talking about, because the phyla only happens all
Yeah.
at once,
Mhm.
or are we talking more specific animal groups?
Well, it's not just referring to animals. So you
Well,
can also do
referring to
plant phyla, fungal phyla.
I only care about the animals.
It's because you are one.
My way to be selfish, Charles. Other organisms want to be known too.
But they're not as interesting. Actually, that's a lie. I shouldn't have said that. Anybody else have any thoughts?
All right, 30 seconds. Wrap up your thoughts. Find yourselves a representative.
That's me, I guess.
I mean, you just have a great way with words. You know how to explain stuff.
So
So
good.
it's like Hitler had a great way with words. You got it. Don't be Hitler.
It's the easiest compound of the discussion.
All right. Wrap up your thoughts. Hopefully you have yourselves a representative by this time. Is it you 8 together? And then it's you 8 together back there? And then it's you, is it 8? Oh man, and then this worked out to be 7? Wow! Everybody conformed to the 6/7/8. You don't know how surprising that actually is, because in my other class that I do this, it never, ever, ever happens. But that's all right. So we're going to start here, and we'll make our way clockwise around the room. And today I'm going to stick with the clockwise. I'll just change our starting point. Okay? I'll change our starting point. So let's start here. What are some thoughts?
Well, from an evolutionary perspective, the young Earth was one of extremities in terms
Sure.
of environments.
Yep.
And so, because there's
Okay.
If certain organisms are more fitting to adapt to whatever environment they can, and others are not, if it's an extreme environment, the ones that are not as fit are very quickly going to be removed from the equation.
Yeah, there is an interesting correlation between environmental stability and diversification rates. So the less stable an environment is, the quicker speciation tends to happen. Okay? So the less stable an environment is, the more rapidly speciation happens. And so there is a nice correlation there. If you've got a less stable Earth than what we experience now, you would imagine that there's the potential for high levels of speciation, especially if you can shift and all of a sudden, maybe overnight or over a short period of time, the conditions change enough to where life is possible, right? They're not so extremes that life isn't possible, so they get to a point where life is possible and the environment is very unstable. So your original life forms, your original survival machines diversify rapidly. Yeah.
We took it from a biblical perspective
Okay.
and just looking at Noah's Ark.
Okay.
And just seeing how there was a bunch of different species, and as they had to adapt to the new environment since it changed so drastically, that could have caused.
So you're thinking in post-flood,
Yeah.
post-flood deposits. Yeah. And so that's okay with just forms in general. You have to be careful if you're going to answer a question focusing on phyla with that, because by the time we get to Cenozoic, our post-flood deposits, virtually all of our phyla are in place. All animal phyla are in place, all plant phyla are in place, probably all fungal phyla in place, but I don't know because I'm not a mycologist. Probably all eukaryotic phyla are in place. And who knows about bacterial I don't even know if you organize bacteria according to phyla. Yeah, I'm sure that you do, but I think that's silly because I don't even think you should organize them according to species, but rather just organize them according to morph, right? Morphology. But anyways, another discussion for another time. But yeah, if you're just going to talk about diversity in general, the reason why you could expect to have some rapid diversification in the Cenozoic deposits, which would be post-flood, is you're basically starting over, right? You're reducing all of the life forms down to a single breeding pair, representing what probably prior to the flood was multiple different forms that we would look at and classify as different species according to a morphological species concept, and now you have to start over. On top of that, some organisms just are not well suited for a post-flood world. Okay? A post-flood world is going to be very different than a pre-flood world, and if you want to talk about that, we can talk about that further, but it's a bit beyond the scope of our discussion now. But yeah, if you just want to talk about forms, why you'd expect to see rapid diversification following the flood or in Cenozoic deposits is, yeah, there are a lot of open areas and a lot of space to fill in, regardless of what your view of origins is. Whether you hold to a global flood or not, the Cenozoic opens up a lot of places because the idea is your dinosaurs go extinct, something shifts, right? At the end of the Cretaceous, dinosaurs stop to exist, cease to exist, except for birds, of course. And so all of those niches that were occupied by dinosaurs are now open up, and mammals move in and take that place, and you see rapid mammal diversification in the Cenozoic, and some in other amniotic groups. Yeah, thoughts here?
You talked about how if there wasn't a flood, how else could we have all of this diversification happen? And if there was no global catastrophe, then there would have to be many local catastrophes.
Right, happening at the same time, which gives you some idea that there is something happening globally, right? So, like, if in every place on Earth that you can access Cambrian rocks, you find an enormous amount of animal diversity that are all basically in the same rock layer, and you're like, well, that's interesting because it takes some kind of a catastrophic event to bury animals so that they're fossilized, and now we're having it happen here in the Grand Canyon, we're having it happen here in other places where you can access Cambrian rocks, and now it's kind of interesting because you have local events happening simultaneously with local events somewhere on the opposite side of the Earth, giving you some indication that something globally was happening, which is an interesting idea. Yeah. All right, up here.
We came with the two different
Okay.
models for the two different theories on the age of the Earth.
Sure.
The first one being the biblical one of the global flood. Basically, what was represented are in the different stages, eras, epochs, whatever, different ecosystems.
Okay.
Of course, that brings up more questions. as
With
well.
marine deposits, primarily.
Primary marine.
Yeah, so that whole, because what you're getting at is like ecological succession, right? So if you're seeing a lot of forms showing up at the same time, it's because you're entering into some kind of a unique ecosystem.
Right.
Yeah, yeah, yeah.
Right. Of course, my question at that point is, especially with the marine ones, how did they stay in one spot, and so that they were buried on top of another, ecosystem.
Sure.
And then the same thing with terrestrial deposits is that they represent different ecosystems. So the Jurassic, they're all different.
Sure.
But then again, I have more questions with that as well. And then with the old Earth model, what you're seeing are evolutionary successions.
Okay, yeah.
So you're seeing, like with the Cambrian, we see the diversity of life rather quickly. And then they start evolving. Through different forms, adaptations, whatever. And then also responses to environmental changes that happens a lot. And that causes more evolution. Some animals survive, some don't. And so it's basically what you're seeing is a succession of evolutionary changes. And that explains why different taxa appear when they do across all of life.
That is true. It doesn't necessarily, though, explain why several taxa show up simultaneously.
At once.
But it does explain why a particular taxon might show up when it does.
Well, the thing is with the old Earth is that when we see taxa appear at once, geologically it's at once, but in reality, time-wise, it could be like 10,000 years, could be a couple million years.
Well, it could be a million years.
It could be millions and millions of years. So to us, it looks like at once, but in fact, it was.
Well, not only to us in looking at you're right about that. Yeah. So I mean, if you're talking about the Cambrian being roughly 50 million years long, right? Roughly 50 million years long. And so if all of the animal phyla show up in the first 25% of that, you're like, wow, that's really weird, right? They're all showing up at the same time, but you're like, in reality, that's 12.5 million years. That's a long time, right? But so it's not just, but that's still, so it's not quite as short of a time. It's not quite an at once as you think of when you think of at once, like boom, everything's there. But in context of trying to extrapolate microevolution to macroevolution, it still is at once. Because 12.5 million years is not enough time extrapolating microevolution, natural selection, genetic drift, sexual selection, gene flow, mutations, to still get the amount of diversity to get all 30 plus animal phyla within that short of a period of time. So even though it's not quite the at once that you think it's at once, it's still at once with regards to trying to extrapolate. Unless, of course, there's some other mechanism. And that's why the way you interpret the fossil record, really regardless of what your view of origins is there has to be some mechanism other than our typical extrapolating microevolutionary mechanisms to explain this rapid appearance of diversity. And so the textbook tries to do that a little bit with the Cambrian explosion, talking about the intense amount of competition and the intense amount of adaptive radiation taking place in these pools. But even that is not good enough. It's not good enough. So you need some kind of another mechanism. And there are some other proposed mechanisms for getting rapid evolutionary change that could account for that. But sudden appearances of several phyla, the way you'd explain it from an old Earth perspective, a naturalistic perspective, is you basically have some mechanism that we haven't seen, that we actually haven't seen in action, developing that level of diversification over a short period of time. And so from coming at this from a young Earth perspective where there is a global flood, the way you explain the sudden appearance of several phyla is you especially a Cambrian explosion, that's the beginning of the flood deposits. So at the beginning of the flood, you bury basically some representative of all of our major animal groups Not all the representatives, but at least a representative of all the major animal groups. And then you're dealing with some kind of an ecological succession. Not quite like driving, through a desert and start climbing up a mountain, right? It's not that simple of an ecological succession, but something like that.
Now, even after the flood deposits, let's go back to a younger
Okay.
perspective. You still see some sort of succession in the Cenozoic.
Oh, absolutely you do. We're going to get there. That's one of our questions.
Okay.
You save that. All right. So this one we're going to deal with a little bit shorter because I think this is an easier question to deal with. How can we explain more derived forms showing up later in the fossil record? So how can we explain more derived forms showing up later in the fossil record? Explaining that from a long Earth naturalistic perspective should be relatively simple. Explaining this from a biblical perspective is a little bit more challenging. But go ahead and take about 90 seconds. 90 seconds to work this out. Group leaders, get everybody's voice heard. 90 seconds starting now.
Same group leader? All right, then. Yes, we'll start on that side.
I hate to do this to you, Dr. Engel, but I have to alert you to something. You spelled Paleozoic wrong.
Yeah.
So there was more, so from the biblical view.
This is also most commonly referred to as the Paleocene.
Okay, cool.
But either is okay. Either's okay.
Okay,
Thank you.
you're welcome. You're welcome.
You could have told me, 30 minutes ago.
That's true. I just noticed it.
More and more forms show that, especially the horizontal gene transfer. The genes will shift from side to side and vertical as well. And this is more and more derived forms.
So from,
As time went on.
sort of the same answer. It's just their adaptation to being able to. So what do you think? How do you start from evolutionary So why?
I want to go for the more difficult. How do we explain it to younger?
Yeah, that's right.
Because it's easy to do it.
Is that those rock deposits exist?
Well, first of all, life on Earth, or on the land, meaning, has more difficulties to begin with than life in oceans. And generally, the younger deposits are marine deposits anyway. So, and if they're not a marine deposit, then they're really close to water. That's why we get a lot of amphibians first. At least we think they're those. Stem tetrapods. I'll call them that.
Basal tetrapods.
Okay, basal. For stem. Anyway. Yeah. So that probably explains why we see simpler ones, because they're generally the younger,
30 seconds.
the lower rock layers are wetter, and the farther up you go, the drier they are. That could mean that the flood was coming upon land and was burying things close in more inland. But then again, I always go back to, well, then why do we see such a succession in marine deposits? I mean, why do we see only certain taxa late in the fossil record that are marine, that are more complex than the ones underneath it? If that makes any sense.
Maybe in that sense too. You do have. You don't
All right.
marine organisms.
Okay.
Layers in the water.
So,
So if you go.
I need to allow you to be a little bit more fully informed. And really, you had everything you needed. Well, not everything you needed, but you had almost everything you needed. I just need to remind you of some things we've talked about already. One of which I'm not going to remind you until we hear everybody's idea. But one of which I am going to remind you, and that oh man, now I'm blinking because gosh. Okay, I got all distracted because I was gonna remind you of both, but then it would actually give you the answer. So then I was like, no, I need to put that one off, and then I forgot the other one. So we'll just start. Okay, we're just gonna start. So we're gonna start here, and we're gonna move clockwise. So we'll start in this group, and we'll move this way. All right. So some ideas.
So basically, like with the old Earth, as you said, it's a lot easier to explain. Just succession of the forms, natural selection, made it more and more derived.
Okay.
Selecting favorable genes.
Sure.
And then, of course, with the young Earth, it's a little bit more difficult. And when we thought about it, we kind of had to, we made a mental understanding that those rock layers exist, but the time scale would be much different with a young Earth.
Sure.
And even that being said, you still see evidence of that. So we thought possibly that there could have been some forms that were just better equipped to deal with the flood initially.
Okay.
And with that initial explosion, some were able to survive a bit. But
Or yeah, sure. Either survive a bit or at least float a little bit longer. Yeah. Because you don't necessarily need to be alive if you can just kind of float it out. So certain bodies are going to sink better than others. Yeah, certain bodies are going to sink better than others. It's not about being killed by waters. It's about being buried under sediment at the bottom of the water. All right.
All right. So we kind of went with more how from a biblical perspective we could see more derived forms and stuff like that. And so Charles brought up a good point where usually you have to rise in water level, and so we see most of our basic forms are marine organisms and stuff like that, and so they probably would have gotten buried first, and then as you go up in different environmental areas and stuff like that, as you get higher up in altitude, you might see more derived forms just getting buried there because you're going up in you're going to get more complex forms as you go onto the land more.
Right. That was one thing I was going to remind you of.
Yeah.
This whole idea of complexity. Remember, more derived does not necessarily mean more complex. That's one thing we've talked about several times this semester. More derived does not necessarily mean more complex. And another thing you have to keep in mind is you have to talk about what are you meaning when you say complex. What do you mean when you say complex? And we also had this discussion, what do you mean when you say diverse, right? And so if you're talking about structural complexity, you're talking about just novel structures, right? A lot of, really highly specialized tissues, really highly specialized structures that you didn't find before. Yeah.
So we went both biblical and evolutionist
Okay.
perspective. So from an evolutionist perspective, it seems like natural selection would make most sense because of the constant changing Earth from a more unstable start to a stable point that we are now.
Yeah.
And then from a biblical perspective, similar to our answer to the first question, is that with the rising flood, that the more derived species were able to survive longer as the water raised.
Okay. Yeah. All right. Same idea. Or maybe not necessarily survive longer, but float longer. Yeah, float longer. Yeah.
We came up with horizontal gene transfer, how that could have given us more derived forms.
Okay. It's an interesting thought, especially when you're talking about Cenozoic forms. This whole idea of horizontal gene transfer, because from a flood perspective, okay, so if we're looking at this from a flood perspective and we're saying, okay, all of this is representing, 6 to maybe 20,000 years, and you're looking at, okay, well, post-flood deposits, we're looking at maybe 4,000 years, maybe longer, depending on whether there's gaps in the genealogies. I think most people are comfortable saying this could even represent maybe 10, 15,000 years of post-flood deposits and still consistent with what Scripture talks about. Because in the post-flood genealogy, it's very easy that you could have some gaps and it could actually represent long lineages. But what you're looking at is when you see forms start showing up, it's very interesting, because even if we're given, 10, 15,000 years in here, it's still, by the time Job writes, you're talking about, Job is what, about 2000 BC, somewhere around that. And so you're talking about 4,000 years ago. By 4,000 years ago, Job is talking about modern mammal forms. He's talking about several species of cats, camels, modern forms. And so which now you're like, in 10,000 years, I have to go from one single breeding pair of the cat kind and basically get all of our modern forms in 10,000 years. That's still a short amount of time. You're like 10,000 years, that's forever. Well, yeah, compared to a human lifespan, but that's still a small amount of time for speciation events, right? Which is an extrapolation of microevolution. It doesn't require an additional mechanism, but it is just kind of a consequence of microevolution. So, some other things I want to remind you of. So, you have to realize that more derived doesn't mean more complex. In fact, it oftentimes means the opposite, because usually in that process of becoming specialized, you lose some of the flexibility. You lose some of that complexity. Another thing you need to be reminded of is a lot of our early deposits are marine deposits, meaning you don't even start finding truly terrestrial forms until well into the Paleozoic. And so there are some forms that you're not going to find. And if the idea is life started in water, any terrestrial form is more derived than an aquatic form, right? Because it had to make that shift. Now then you're like, well, what about secondarily aquatic forms that were terrestrial forms and then moved back to water, right? Like what about crocodilians or marine iguanas or sea turtles? That taking out of the equation, there's going to be the idea that a terrestrial form is going to be more derived, right? So that makes sense from a flood deposit. You're not going to start getting terrestrial forms until later in the deposit. The absolute most essential thing you have to remember about coming to this question from a biblical perspective and a young earth perspective is that fossils always appear simpler than what the organism was during life. Always. Okay? No matter how old the fossil is, it always appears simpler than what it appeared in real life. Okay? And the deeper that rock is buried, the more extreme that relationship is. Because the deeper the rock is buried, the more force, the more pressure on the organism buried in that rock from a longer or a deeper column of rock on top of it, and the more it experiences seismic activity, the deeper those rock layers are. So the deeper the rock is, the simpler the organisms are going to appear compared to what they actually appeared like when they were alive. Meaning your older deposits, it is highly likely that those organisms were a lot more derived than what they appear. Let me get Joey first and then we can come over here.
So,
Just run out of time.
so when you look, so like the Bible says that they were supposed to bring all like the terrestrial animals in the ark, but it didn't say anything about the fish.
About marine forms, yeah.
God intended that, terrestrial forms have to repopulate the earth, but the fish wouldn't have to repopulate. Some of them
Sure.
would survive the flood.
Right.
How does that affect the way we?
Well, so you're given more time. You're given more time for some of the diversification. So it's highly likely that our marine forms didn't lose as much diversity as the terrestrial forms did.
There wasn't as much of that bottleneck effect.
Yes. Yep, absolutely.
So you're saying that animals that look simpler because of seismic effect on
Yeah, a fossil is always going to look simpler than it did in real life. Most of your synapomorphies disappear. So like when you're looking at, let's say you took, let's assume just for, kicks and giggles, right, that all of your mollusks root back to a single survival machine, okay? We'd have those that we would consider to be more derived would be like cephalopods, and those that we would consider to be less derived would be like chitons, polyplacophorans, okay? And let's say you took both of those forms, like you took a cephalopod and you took a polyplacophoran, and you bury them and you fossilize it. A lot of the things that make cephalopods unique in their individual groups are not going to fossilize well. Now, that's not to say we don't have good records of cephalopods. We do, but a lot of it is based on some of the harder objects. So the synapomorphies tend to disappear during that fossilization process, and you're left with a lot of the ancestral traits.
Now you have a lot of animals that are found today that are buried, deep within the time scale, and they look pretty much the same. Things like coelacanths. Like I can't remember when coelacanths first appeared. Actually, I just don't know. But it's pretty early in Earth's history, and yet they look the same.
Skeletally.
Skeletally.
Yeah, and then you have to infer other information about, like, what did they use their swim bladder for? Did they use it like modern coelacanths do? What about the nervous system and sensory structures? Was that like modern coelacanths? So yeah, skeletal features, and those are the plesiomorphic traits.
Yes.
The plesiomorphic traits are the hard skeletal features, and a lot of those, yeah, absolutely, you can see. And other things is fur, because the skeleton looks a lot similar. All right, we're obviously out of time. Have a wonderful weekend, a wonderful Friday. Charles, we can continue this discussion.
Yes. Okay. So, and then you have placoderms, giant